Hi, 7th grade Trailblazers. All right, let's start talking about waves and light. So we're done with scientific method, and we're going to get into new stuff. So hopefully you're taking notes, and you're ready to start. All right, we're going to start talking about waves. And the first kind of waves we're going to talk about, not ocean waves, not waves like that. We're going to talk about electromagnetic waves. And so what electromagnetic waves are is that they are a disturbance. So a wave is a disturbance because we're disturbing the material or the space around them that involves the transfer of electric and magnetic energy. So waves transfer energy, whether they're electromagnetic or they're ocean waves. So electromagnetic, and I'm lazy, so EM stands for electromagnetic waves, is made up of vibrating electric and magnetic fields that move through space. So that's important. They can move through space. Or air. So that means a medium is something like air, and they move at the speed of light. So let me show you what an EM wave looks like. Let me get my YouTube video going here. And this is what electromagnetic waves look like. So look, we have cool things coming out of my electromagnetic wave. So that's definitely what it looks like, and this is going to play for a few more seconds so you get an idea of the movement of the electromagnetic wave. All right, back to our thing. So vibrating electric and magnetic fields that moves through space or some medium at the speed of light. So the energy that EM waves transfer through matter or space, remember they can move through space, this is important to know. Because like sound waves can't travel through space. Sound waves have to travel through matter. Electromagnetic energy waves don't. They can travel through space. So those waves are called, those waves are pretty cool and unique. All right, so how do electromagnetic waves compare? Now, we can compare all the waves on the spectrum by using some pretty interesting things. The first thing is wavelength. How long is a wave? How do we do this? We measure the distance between the crest. The crest is the top, so that's good terminology to know. The bottom of a wave is called the trough, T-R-O-U-G-H, trough. So top is crest, trough is the bottom. So to measure the wavelength, we measure from one crest to the next. So some electromagnetic waves have long wavelengths, meaning the distance between the two waves is long, and some have really short, like we see over here. Now, what also goes into that is frequency. The frequency of a wave is the number of waves that pass a given point in a certain amount of time. So if we look at a long wavelength, it has a low frequency. So if I measured my distance from here to here, we can see that not many waves pass through that. Now, if I do that same distance over here, we have a higher frequency because more waves pass through that space in a specific point of time. All right. All electromagnetic waves, this is interesting, travel at the same speed in a vacuum, meaning a vacuum is like space. But because they have different wavelengths and different frequencies, they're going to seem that they, move a little bit differently. So light and all EM waves travel at the same speed, and it's called the speed of light. Ta-da! In free space, like vacuum space, light travels at an incredible rate. Now, when those EM waves hit something like Earth that has matter or air, they're going to move a little bit slower because they have to pass through it. So light can travel around the equator of Earth 8 times in a second. That's crazy fast. All right, so the electromagnetic spectrum is made up of different types of waves that increase in order of frequency. So we start off with radio waves that are really low frequency, and we move through microwaves, infrared rays, visible light, and by the way, these are the only wavelengths that we can see of the electromagnetic spectrum. UV light, X-rays, and then finally gamma rays. All right, so let's start with radio waves. So EM waves are the longest wavelength and lowest frequency are radio waves. Now, because radio waves are so long, they have that long wavelength, they're able to travel really far. So, like, you can, if you have a really good radio with a really good antenna, you can pick up radio stations here in Florida from other countries across the ocean. So we use radio waves for broadcasting, for radar, for satellites in space. That's how we talk to a lot of our satellites that we launch is using radio waves. Next is microwaves. Now, when we think of microwaves, we think of a microwave oven. And microwave ovens do use microwaves to cook food, but your cell phone uses microwaves. So it's a type of wave that is used to cook food, to transmit our data over cell phones. We use it for radar. So they're a little bit shorter wavelengths than radio waves and have a little bit higher frequency. Then we get to infrared rays. They have higher frequency and more energy than microwaves, and we use infrared rays for like heat lamps. So like at a restaurant, if you ever see like, at McDonald's, they'll dump the basket of fries that just came out of the fryer into that, French fry collector. And on top of it is heat lamps. Those are really infrared rays that they're using to keep your food warm. Cameras, so we can see Kitty over here. Kitty, we can see most of the heat of Kitty, or most of the energy from Kitty is contained in its torso, which totally makes sense because that's where all of Kitty's vital organs are. You can see his tail and his little feetsies and his little ears and nose. They have a less heat coming off them because there's no organs there. There's no reason for the body to direct a lot of heat there because they're not keeping organs safe. Next, we have the visible light spectrum. This is the only type of wavelengths we as humans are able to detect. So our eyeballs are only able to see the visible light spectrum. And visible light that appears white is actually a mixture of many colors. And we're going to watch a video at the end of this that kind of explains visible light a little bit better. Okay, moving right along are ultraviolet rays, or UV rays. And so just these waves are just a little bit shorter than visible light rays, and our eyes can't see them directly, but we can sure feel them. So when you're out on a sunny day, UV rays are really what can cause damage to our cells because they have a lot of energy. So, but don't think of UV rays as all bad. If there wasn't UV rays, your body would not produce vitamin D, which is useful for bones. If you didn't know that, you do need it. So, sunlight in small doses is good for us, but you should wear sunscreen to help protect you against UV rays. All right, X-rays. You guys at some point in your life have probably had an X-ray taken. So you go to the dentist, they want to x-ray your teeth because they want to see if you have any cavity creeps living in there. So they're going to direct these x-rays, which you can't see them because our eyes can't detect those waves, but we are able to use those images of bone and teeth. Now, these are also damaging. That's why when you go to the dentist, they put that lead kind of like cape thing over you to protect your organs so those x-rays don't hit it. So we don't go out and hang out in an x-ray lab just to party because that stuff is not good for us. The first pioneers or scientists that really worked with x-rays died of cancer because of the damaging effect these rays can have on the human body. All right, last but not least on the electromagnetic spectrum is gamma rays. So these have the most energy, so they have the shortest wavelength and the highest frequency. Really, on Earth, we artificially manufacture or use gamma rays. We use it in nuclear medicine. So over the summer, Miss Marshall was sick, and I didn't know what was wrong with me, and I knew it was something with my digestive system, and I actually had to get a nuclear medicine which used gamma rays. So it was pretty cool. So I sat there, and they injected me in an IV of nuclear medicine, and then they put me in this machine that fed gamma rays to it, and the gamma rays were able to detect where that medicine was going in my body, and were able to say, your gallbladder, it's not working, Michelle, you need to have that sucker taken out, which I did. So we do use gamma rays here on Earth, but that's not something they do to you a lot because it's not good for you. It can cause long-term exposure can cause cancer and other health defects. Now, gamma rays are emitted by a lot of high energy objects in space, so we make telescopes that are able to read gamma rays so that we can look at these pretty cool images. All right, so that's it with that. We're going to watch a video on color. This is a pretty cool video, and it helps to explain exactly what color is. So let me get my pointer going. Bye-bye, laser pointer. And let's watch the video.
One of the most striking properties about light is that it has color. To understand the phenomenon of color, it helps to think about light as a wave. But before we get to that, let's talk a little bit about waves in general. Imagine you're sitting on a boat on the ocean, watching a cork bob up and down in the water. The first thing you notice about the motion is that it repeats itself. The cork traces the same path over and over again, up and down, up and down. This repetitive, or periodic, motion is characteristic of waves. Then you notice something else. Using a stopwatch, you measure the time it takes for the piece of cork to go from its highest position down to its lowest, and then back up again. Suppose this takes 2 seconds. To use the physics jargon, you've measured the period of the waves that the cork is bobbing on. That is, how long it takes a wave to go through its full range of motion once. The same information can be expressed in a different way by calculating the wave's frequency. Frequency, as the name suggests, tells you how frequent the waves are. That is, how many of them go by in 1 second. If you know how many seconds one full wave takes, then it's easy to work out how many waves go by in 1 second. In this case, since each wave takes 2 seconds, the frequency is 0.5 waves per second. So, enough about bobbing corks. What about light and color? If light is a wave, then it must have a frequency, right? Well, yes it does, and it turns out that we already have a name for the frequency of the light that our eyes detect. It's called color. That's right, color is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly, like we can with the cork in the ocean. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its color, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of color called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colors of light, so light of all colors is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colors. What happens to the blue, purple, and red light? They get absorbed, and the energy they're carrying gets turned into heat. It's similar with objects of other colors. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect all colors of light, while black things do exactly the opposite, and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favorite Metallica t-shirt on a sunny day.
Alright, 7th grade Trailblazers, I'll see you in class. Have a good week.